Okay. Yes. So, in the previous class, that was yesterday, we had covered domain adaptation method, specifically a unsupervised domain adaptation method. And before that, we have already seen a supervised domain adaptation methods. And after this, we'll be starting off. I mean, very with a very brief discussion on semi-supervised learning. We'll look at one specific method for semi-supervised learning. As the name suggests, it's neither a fully supervised learning nor it's a unsupervised learning. Supervised learning will have the entire training data is fully labeled, whereas unsupervised learning will be the other extreme. That is, none of the training data will be labeled, and semi-supervised is somewhere in the between. Their method is usually found in yeah, thanks. So, semi-supervised learning basically somewhere in between where you have both labeled as well as unlabeled samples. Now, the problem is that if you build one single network that is supposed to work for both that supervised as well as unlabeled as well as labeled data, it's a tricky thing to do because if you consider unsupervised learning, the task that you can perform using unsupervised learning, classification is not one of them. So whereas your objective over here is basically say some sort of supervised learning, which is maybe classification or maybe a segmentation, whatever may be the case. But in either of these cases, we cannot directly utilize an unlabeled data because you require some sort of a target label. Whether if it is classification, you require a target uh, class label. Whether if it is a segmentation task, then you require a segmentation mask, ground truth segmentation mask. None of which are available if your data is basically unlabeled. Okay. So in order to design a setup that can utilize both of these types of data simultaneously, you have to be a bit uh, inventive. I think we have seen some portion of it maybe in the previous example of say unsupervised domain adaptation, where we used a common network for both types of data, but we'll be doing something similar maybe, but a slight difference that we'll also be labeling some of the unlabeled samples as well, so that we can use it in the standard cross entropy pipeline for say classification. Okay. So, and the entire idea is that we could have simply sat down and said that, okay, I'll discard the unlabeled data and only use the labeled data. We here say that we'll not be doing that. Will not be taking a shortcut like that. We'll obviously train on the labeled data, but we'll also try to extract as much of information as possible from the unlabeled data as well, so that at the end of the day, we are able to get a better performance than say simple supervised learning on that particular data. And also because there's another factor that comes into play, that in many setups you'll have a lot of unlabeled data available compared to the amount of labeled data available. So is there a way that we can avoid labeling that unlabeled data, the entire set of it, and rather use it in that original form itself in order to reduce maybe cost or time requirements or whatever may be the case. Okay, so we'll look at a very famous semi-supervised learning approach known as co-training. In fact, it's actually the original method is actually very old. It's from '98, but in those days, it was not specifically meant. It was not specifically designed for say deep learning applications. It was, using very basic form of say neural networks and other things. And I think initially it was designed for basically, I think classifying web pages or something like that. It has now become very, mainstream. You will see a lot of methods that mention co-training, and because it's now a basis of many reasons and supervised learning technique. So we'll discuss the core idea behind it, which is actually very straightforward, and that core idea holds true even for recent semi-supervised learning method. At least a lot of them, it still holds true. Okay. So, before we start, the core training supervised approach has some assumptions. So, first of all, if you can look in the diagram as well, you can see that there is something known as V1 and V2. Okay, it's nothing but every single instance in your data will be considered to have two different views. Okay. Now, we'll come to how to get different views, but the general idea is that suppose if I give you an image, I can maybe apply different augmentation technique or transformation technique to create two versions of the same image. So if the original image had a class cat, even after augmentation, the both these augmented images or augmented views will still belong to the cat class only, but there might be some difference in the visual representation of these two views. So first of all, every data point has two views. I mean, you can also extend this idea to multiple views, but for now, let's consider two views. And every view individually is sufficient to learn a good model. For say, if you're learning a cat classifier, every view should be individually good enough. So you don't don't apply such augmentation that the image itself becomes meaningless. You don't do that. And if you don't do that, you still have information about the cat in both types of views. So individually, each of these views can be used to create a good model for cats. Okay, yeah, as an example, it can be for any other things as well. Okay, and finally, when you train your model, say you have two models that are being trained separately on V1 and V2, these two views of this data, then their predictions also will be consistent. So your prediction of F1 on V1 will be same as your prediction of F2 on V2. That's the assumption. So it's not that after this augmentation, the code information has not changed. If the code information is not changed, both of the classifiers which are trained on these different views will still predict cat. Okay, it's not that it will suddenly start predicting dog. So these are the standard assumptions that they make. And based on this, it proposes a sort of a dual training, dual view self-training method where you are separately and parallelly training two views on say two networks, and then helping each of these networks will help each other train better. So that's why the term is known as co-training, because there'll be two networks. I mean, you can also extend this idea to multiple networks, and each of these networks will help the other network in maybe performing well on your standard samples that are already labeled, because it's semi-supervised setup, and also it will help label these unlabeled samples for the other your networks as well. Okay, we'll see the exact example. Exact details of this algorithm, but it's generally it will be this idea. Okay. So the idea is that you learn a separate classifier for each view. Okay, and then the prediction of the two classifiers on the unlabeled data are gradually added to the labeled data to continue the training. So you have your set of samples that are in S, which are labeled, which is the supervised data, and you also have say some unlabeled data present in your unlabeled samples. And as per our assumption, every data point, whether it's in the supervised set or in the unsupervised set, has two views, V1 and V2. So what you end up doing is that you train one classifier on V1, okay, and one classifier on V2, and after that you utilize the first classifier to label some of the unlabeled samples for H2, and use H2 to label some of the unlabeled samples for H1. That way you're also increasing your labeled sample list, and over time you'll observe that your the models are able to utilize both your labeled data and your newly labeled samples that has been labeled as self-labeled samples by the network.
So like C by C2 we are labeled to C1. So if information is very correlated, then we are able to label, right?
Yes, because it's the same data. That was the assumption. The assumption is that you have data, every data point which has say two views or say multiple views, but the views are in themselves sufficient enough to learn a good model. And also, even if you have trained two separate models on these two views, these two models will have a consistent prediction. So the prediction on say if you have a model an image X with two views V1 and V2, the prediction by the first model and the second model will basically be consistent. It will predict the same class. That's the assumption.
Because it's a semi supervised, so we are taking the opportunity of C2 to labeled on C1, right?
Exactly. And we are doing this for different views, because unless until we use different views, if we would have used the same X for both these cases, then they would have both learned the exactly same set of weights. Okay, and then there is no point it will not be as helpful in using one network to label the network or label the unlabeled samples for the other network, because they will essentially be the same network. So in this way, by utilizing different views, you're ensuring there is some difference. Maybe one of the network learns to identify a better property and the other learns a different but equally important property, and then based on that you're relabeling the samples across them. And that way this training progresses, and your supervised set always gets augmented by these newly labeled unlabeled data, and you're utilizing both kinds of data. Right. So we'll look at the algorithm. It will basically be the same thing which I described, but this will be in much more detail. So you're given a set of labeled training examples. You're given a set of unlabeled training examples. You'll create a pool of by choosing, say, a few of the unlabeled samples from the unlabeled set. Okay. And now what you'll do is that you will run multiple iterations of this particular process. You will use the label training examples to train the classifier, say the first classifier H1, which only considers the first view of X. Then you'll use, so this will be correct, this will be classifier, simple error. Okay. Then we'll use the X2 view to train another classifier H2. And then what you'll do is that you will use H1 to label the X2 views from the unlabeled examples that you've chosen in U dash, and you'll use H2 to label the X1 views of the samples that are present in your U bar. Okay, so you're doing sort of a cross labeling using your trained models. And what you do is that once you have labeled the samples, now these are your newly labeled samples, simply add them to your label training set, because now you have labeled them, and you have lost some samples from your unlabeled set to your labeled set. So you replenish your say random choice of, say, random examples, random unlabeled examples. And you do this thing, you again repeat this process. So what happens that over time, all of your unlabeled samples will get labeled by your these two models that you're training parallelly. And over time, you're able to utilize both your labeled examples, and you have actually also performed labeling of the unlabeled examples without using any human expert. So that way also you're parallelly solving two tasks at once. You're also solving for this particular task, whatever task it is, maybe classification, and also you're performing labeling, automatically labeling of the unlabeled samples as well. Obviously, I mean, the entire idea behind any sort of this process is that you're assuming that these two models will be able to properly identify the correct labels for the unlabeled samples, which might be a bit tricky. So maybe you can hold out on the labeling part at least till both of these classifiers have run a few epochs initially on only your, say, labeled examples only, so that once they have start giving some good, say, training accuracy at least, only then you start labeling the unlabeled samples, so that you don't get garbage sort of labels initially if you try to do it initially. And then as the time progresses, both of them are helping each other to train better. Okay, so that's a very standard semi-supervised learning technique, which, yeah, I think someone has a question.
Sir, the creation of X2 from X1, that is a transformation that we do. We create it ourselves, right? I mean, it is.
So yeah,
create the second.
So there are different ways of creating these two views. The thing is that suppose, just a second. Yeah. So there are various ways of creating your two views from X. So for images, it's very straightforward actually. So what you can do is that you can apply two different types of transformations. So once suppose you perform a rotation by 90 degrees in one of the images, and in the other images, suppose you create a black and white version of it, or maybe you rotate it by some other angle. So it's the same image. If it's a cat image, it's still a cat image, but suddenly one of them has looks a bit different. So the models that are getting trained on them will have to work differently in order to extract that cat information from both of these images. So that's one way of dealing with it. You apply some augmentation. Other approaches also include, say, what you can do is that you take the same image, you don't create explicitly two views, but you pre-process these image, not pre-process, but you pass this image to two different set of subnetworks for these transformation subnetworks. So what they do is that they are convolution networks only. You will extract some features from them, but these two will be of different architecture. Maybe one has 3 convolution layers, one has only 1 convolution layer, And as a result, the features that you get will maybe of different size, but maybe of different dimensions and all. So that way, you're extracting two different types of features in a way, because the dimensions and other things are aspects are different from the same image. And then you start with this training these two different models. So that way also you can consider that these are two different views of the same models.
You can
Once
use
this portion is done, the rest of the network is again the same. There are two copies of the same network, but the initial portion may be a bit different.
Sure. And we can use autoencoders with different dimensions also, right?
Yes. No, autoencoders will recreate your image. If you use only the encoder portion.
Yeah.
Okay. Yeah, that's right.
Different dimensions. So what if H1 and H2 give us a separate label?
No. So that's the whole point. So what will happen is initially, obviously, these classifiers are not trained, so they may not perform that well. So the idea is that you wait for a few epochs till these classifiers start predicting the correct classes on only your training set, on your label set. So what will happen effectively is that once these classifiers start working, maybe it's giving 80% training accuracy at least on the training data, that occurrence of, say, inconsistent labels, that occurrence will go down a lot. Okay. Obviously it's may not be 100%, but a lot of the problem will get sorted out once these classifiers have become good enough themselves. Okay. And since you have not made any such major change to the network, to the images, such that the code information, maybe if it's a cat image, it's no longer a cat image, you have hidden maybe the regions of the cat. If that has not happened, then the idea is that your both these classifiers will still be giving consistent predictions.
Sure, sir. Yeah.
Okay, so with this, we'll move on to our next topic. So we are done with the semi-supervised learning topic. Any questions up to this point? We'll start off with the model compression part.
Sir, how do we calculate this confidence? Like, is there a score that...
Okay, forgot to mention that. Yeah, so confident, right. So suppose you have a set of samples in your U-bar, unlabeled samples, and you're applying your H1 and H2 to get the predictions for those. Now, the idea behind this particular technique is that you don't label those samples for which your model is not confident. How to find the confidence? What you can do is that you can consider, say, for a given example, your H1 produces a set of outputs. So suppose there are 3 classes, you have an output like this. So you have, say, one case of, say, 0.7, you have another 0.1 and 0.2. And for another sample, you have maybe, you have, say, 0.5, 0.3 and 0.2. So the general idea that it's sort of a heuristics only. It's not a very done deal. So what you can do is that you can get the entropy for this particular setup as well as the entropy for this setup for, say, 2 images, X1 and X2. Okay. Now, if the entropy, if one of these predictions is not very high, the entropy of this particular setup will actually be high. Okay. And if one of the predictions is very high compared to the others, the entropy will be low. Okay. So what you can do is that you can sort all the samples. Suppose you have, say, 100 unlabeled samples. You sort all the samples based on the entropy of the predictions that that was obtained on top of them. And maybe you take the first 20 samples, which has the lowest entropy, which means for those you have the say you have predictions which have one of the classes which is very high say probability within that particular prediction. Okay, this is not necessary that this will always work fine, but by restricting your choice to only those cases where your models are making predictions with very high probability for the particular class, you're reducing chances of labeling those samples for which your model is not working that well. Your model is not able to differentiate that well between all the classes. So that's one way of looking at confidence, though it's still a heuristic. It's not a specific thing that will always work. Another way is if you simply look at what is the percentage that you're giving to the predicted class and you set a threshold. So if my predicted class has a probability of say 0.7, I'll consider my prediction to be confident, something like that. So there are different ways you can attack the same problem. I have just described two of them. Okay.
So, sir, like once we, I mean, so you said like maybe top 20 or whatever examples we take. So we label those, and then in the next iteration we add them to the label set and again retrain.
Yes. Yeah, that becomes part of a label set, and you replenish uh, the the bucket that was empty. This suppose you lost 20 samples from your unlabeled set, so you replenish by another say 20 examples from your unlabeled set. Okay. Right. So we'll move on to another interesting concept that becomes very handy in deep neural networks. As you all know, deep neural networks require a lot of, if you want a good performance on some standard data, you will require a lot of parameters along with it. With large number of parameters comes in a lot of problems along with them. You require better storage space, you require more processing power. In fact, when the amount of storage space that you require may become insignificant compared to the amount of space that you require when you're actually running that model or using that model for inference, because of the intermediate outputs that you generate. That actually increases. So if you run it on say any GPU, you'll see some of the models even say 40 or 50 MB models taking up 6 or 7 GBs of space in your GPU memory. So that's the core concept behind, the core reason why we are looking at say model compression. um, as I'll just go through these points, deep neural networks have become very popular for different tasks, and models have become more and more complex. If you look at the initial, say, fully connected networks, then we had your standard convolution networks with a few, say, fully connected networks at the end, fully connected layers at the end, and then you came up with much more complicated. Say you started with LXNet, you move on to say ResNet, you had DenseNet, now you have a lot of things, and the models are keep growing in complexities, and the size of the models and the computation requirement of these models have also grown exponentially along with these new set of models. So for various say real-time tasks or say edge devices, it becomes very tricky for you to deploy a large-scale model which may be performing very well, but may require a lot of processing time. And the assumption is that and also maybe your edge device or whatever device you're trying to deploy your model to does not have that much of say high-speed computing power, does not maybe have a very low-end GPU or maybe have a low-end CPU only. And then what do you do to basically still be able to run such a model on top of it? Okay. So model compression techniques have been in play in the recent years, and people have been looking at different ways of compressing the models. We'll discuss some of the ways of doing that. Okay. Right. So this is just a feel of how your models have grown in size or maybe grown in amount of computation required. So as you can see over here, even though if you look at the parameter size, there are networks which have a lower parameter size, maybe intermediate. Say suppose you have a ResNet 152, which uses maybe in terms of say, if you store the model in terms of the storage space might require slightly less memory than as compared to your AlexNet. But if you compare the amount of floating point operations that you require, or number of operations that in order to process even a single image that you require, you'll observe that there's a 10 times increase or more than a 10 times increase in that. So you require a lot of computing power. Also, another thing that is maybe not visible from here is that ResNet 152 has 152 layers. So each of these layers will have some intermediate outputs when you pass even one single image, and that intermediate output also has to be stored during the processing at least. So, and that what ends up happening is that you'll end up using a large portion of your say RAM memory or say GPU RAM memory, whatever memory you're using, and all of these things becomes maybe costly for some systems of some scenarios, or maybe too much to deal with for some say low-end memory or low-end edge devices, and we need to somehow deal with this problem. So it's not that we have simply increased the size of the models. We have also seen there is a drop in performance also. So you had an error rate of AlexNet, I think, on ImageNet of say 43.45%. Now you have an error rate of only say 23% in ResNet 152, and these are all for say 512 plus 512 plus. Okay, right? And I think this is just an example of what a compression could do for you. I mean, model compression can do for you. So, for example, if you have ResNet 50 and which requires same 98 MB storage space, and if you're using a 2 cross 224 plus 224 image instead of a 512 plus 512 image, you will be using 3.8 billion floating point operations, or say GFLOPs. And if you can apply a good pruning algorithm that reduces some of the redundant weights in your networks, by the way, all of your networks that you use, which are specifically, I mean, the larger networks, they learn a lot of redundant parameters which can be left out and maybe used to reduce the size of your network. I mean, based on that only, we'll be seeing some of the techniques to basically compress your models. And you can actually get this idea from another concept. I think, I'm not sure whether this was covered or not. That is the concept of your dropout layers. If you see what dropout layers does is that it randomly drops some of the neurons during training, and your model is still able to perform well on say given task. And the idea is that whenever you train a deep neural network, there will be a lot of redundant information stored in the weights that you're learning. And so we must be able to safely remove some of these weights, or nullify some of these weights, and reduce the number of learnable parameters without affecting our performance. Okay. So one standard pruning algorithm was able to reduce the number of parameters by a very large ratio of say 75%. And as a result, the model that you then got had 75% fewer parameters, as well as the computational time was 50% less. You have to understand that whenever you are using these sort of heavy end models for any real-time task, suppose you want to run this ResNet 152 model, which might be very good in terms of say ImageNet getting say only 23% error, but you want to run it on say a video which has a very high frame rate, say you have say 50 frames per second, you can every millisecond then counts. I mean, you cannot allow the model to run for even a millisecond longer than required in order to give your prediction. Otherwise, your processing for your every frame will take a lot of time, and overall your entire pipeline then gets affected. So we'll see some of the model compression techniques that helps us to compress your deep neural networks. There are different approaches for it. We'll discuss each of them in detail in the later slides, but generally you can consider these approaches. One is the model pruning, which, as the name suggests, it's sort of like pruning your tree, right? You prune out say different branches, something like that in your tree. The model pruning does something it similar. It will zero out some of the parameters, okay, or maybe delete some of the entire filters itself of different filters. I mean, zero out the entire filters itself, and in a way you're trying to reduce the computations in the amount of memory that you might require for processing any given say input.
But
Another
pruning,
yes
pruning means
yes
he will remove the branches which is not that is dead in case, right? For many
not
branches.
dead necessarily, because see, all this specifically a pruning technique is applied to a trained model. So suppose you have a trained model that is performing somewhere say with say 80% accuracy or so. What you can do is that you can look into the individual parameter weights. Suppose you are only using say fully connected layer, so you have say at a particular layer you have say 100 nodes, and the next layer suppose is another 100 nodes. So what you can do is that you will try to look at a specific node and maybe drop it once and see if the performance of the network is getting affected. That's one technique of pruning. It's not necessarily the technique we'll cover. So you drop it fully, and obviously if you drop one node over here, the connections from that particular node to the next layer also gets affected, and so on and so forth. So then you see whether your model has been affected or not. Or maybe if you have some tolerance, maybe I am willing to suffer say of 1% or a 5% drop. So if my performance does not drop beyond that, then I'm fine. I'll drop that particular node. And so I have pruned your model. I have pruned say significant portion of your that particular layer. I can do this for all layers, and once I'm done with this kind of pruning, maybe my performance drop overall has become say maybe 10%. So what I do is that with that reduced set, I fine tune that network a bit more on the same data and maybe recover some of the lost performance. And that's the general idea you will see for say model pruning. You delete some of the weights, and then you might have lost some performance matrix. You retrain it and a bit, and then maybe regain that idea. And that's the general idea.
Even though some redundant things also possible, right? Which
Yes. So that's a general, core idea behind pruning, that it expects that there are redundancies in your network, and that's why it's able to remove some of the parameters without affecting the model performance by a large extent.
got it. Thank you.
Okay. So right. Another idea is the concept of parameter quantization. So generally, you have say these parameters are real numbers are stored using floating point storage, maybe 32-bit storage. Each of these numbers are getting represented using that. So you can quantize these values and maybe reduce or maybe update these values in such a way that you can now use maybe lower, say 8-bit integer representations, and we'll see how to basically go about that. But the general idea is that you create say maybe buckets within that entire range, and suppose you have a real range weights ranging from say minus 250 or say minus 1.5 to plus 2.5. And then what you do is that you maybe divide it into buckets, and each bucket gets assigned a single number, maybe an integer number. And so that you're now able to use an integer representation and not necessarily a high range integer representation, maybe a low bit, maybe an 8-bit integer representation. And in order to represent these individual values. So obviously you are still losing out on some information because you're not doing an exact weight. So you might again require to retain this thing a bit and maybe regain some of the performances. So that falls under quantization. We'll look at a very basic technique of performing quantization. Another approach is known as your low rank decomposition. And the entire idea behind low rank decomposition is that any sort of layer that you take, suppose it's a convolution layer or a fully connected layer, at the end you have parameters in the form of say a 2-dimensional matrix or a 3-dimensional matrix. And what you can do is that you can suppose it's a m cross n matrix, and m and n are very large. And whenever any input comes, say input of say k cross k is coming to you, this matrix will have to be, obviously this has to be consistent for you to multiply these two things. But anyways, ignoring that, you have to multiply these two matrices in order to get the output of that particular layer. And that will require a lot of computations. So the general idea behind low rank decomposition is that you approximate this very large matrix using two matrices, which are of say a smaller size, maybe m cross 2 and 2 cross m. And what will happen effectively is that, by the way, if you multiply these two things, you still get back your m cross n matrix, but your learnable parameters has reduced by a very large extent. We'll see one example by how much that particular reduction happens. And then what you do is that you simply pass that particular k cross k image and multiply it with these two matrices one by one. Okay, and effectively that reduces the number of multiplications or operations that you require to perform by a huge extent. It will reduce it by a very large extent. And as a result, you have reduced two things. You have reduced the storage space required for storing these parameters because the number of parameters itself have gone down. And also you have reduced the processing time for performing these intermediate multiplications that you require for, say, passing an input through that particular layer. So that's why it's known as a low rank decomposition. You must have looked at some SVD techniques or other things in your, say, machine learning course. We'll briefly touch on that same idea as well, because again, low rank decomposition are based on decomposition techniques that are generally, related to, say, singular value decomposition or something like that. Okay. That's another way. Another way which you have already seen in very detail is that of knowledge distillation. If you remember, knowledge distillation was basically you had a teacher network, which was generally a very large complex network, and you had a smaller student network. Okay, and the idea was that once your teacher network is trained, you train a student network, which will be trained using your standard, say, classification laws, but it will also try to mimic the exact output of your teacher network. or not, if not the exact output, exact distribution of your teacher network for that given image. So it was found that using this process, you can actually come up with a simpler model that has much less parameter than your parent, but performs maybe very close to your parent model or teacher model. Okay. But in a way, what you have done effectively is that uh, your performance remains almost the same, but your parameter number of parameters or the complexity of model reduces significantly. So that's a very simple way of performing your compression. I mean, you're not doing exactly a compression, but you're training another smaller model that has the same property. Yes, anyone has a doubt?
So, so in real industry level, I think we can combine the parametric quantization with QLoRa and then knowledge distribution, right?
Yes, you can do that. You can do that. I mean, these are approaches, individual approaches. You can come up with hybrid approaches to achieve the same thing. That's fine. Okay. Right. And another approach that doesn't get talked about that much as directly falling under model compression, which is basically you use some techniques techniques or layers within your, say, in order to better design your deep learning network. So you must have heard of, say, mobile nets and others. So you can use some techniques to reduce the amount of parameters by intelligently designing the intermediate layer. So we'll look at some of these approaches. Okay. Starting with, say, model pruning. The idea behind model pruning, again, is to remove some unimportant or redundant parameters from your model so that you can then reduce the number of parameters that you need to actually maintain for that model. There can be two types of pruning. One is a structured pruning, and there is unstructured pruning. Structured pruning, what is that does is that if you have, say, a layer with, say, 4 nodes, another layer which has, say, 2 nodes, and these are, say, fully connected layers. So obviously you will have connections like this, okay, right? And suppose the learnable weight is actually 4 cross 2. So you have 8 parameters in this particular setup for your fully connected layer. In your structured pruning, you will not try to delete individual single of these parameters within this particular setup, and instead what you'll do is that you'll try to remove an entire, say, node from one of these layers. So if you remove this entire node, number of weights that you're deleting is actually 2. You're deleting 2 weights from here. So it's structured in that way because you're not deleting individual one parameters from here. Instead, you're deleting one particular node, entire node from a particular layer, and then you're seeing whether the performance is getting affected or not, and so on and so forth. Okay. What advantage a structured pruning has is that even so, since you're not randomly deleting, say, the other option is the unstructured pruning, which I'll say maybe show first so that you can appreciate structured pruning. So suppose how many do we have over here? Just a second. Suppose you have 4 cross 2, right? Yeah. So I'm considering the same case. You have 2 network and 2 layers basically, and you have a learnable weight that is of size 4 cross 2. So an unstructured pruning, what it will do is that it will prune individual parameters. So what it will do is that maybe it will zero out this and this. Okay. And as a result, what will happen is that when you're trying to perform any sort of operations on this particular layer, at least between these 2 layers, you cannot necessarily delete these 2 things. You cannot, because what you have effectively done is that you're using a matrix. If you delete these 2 points, the matrix size itself will become inconsistent. You will not be able to multiply with the input image or whatever input information you're getting. And as a result, even though the number of operations may get reduced because you're doing a 0 multiplications, you may not be able to, because today the GPUs that you use or any sort of, say, framework that you're using are heavily accelerating the performance of these models by utilizing some optimized version of matrix multiplication and other things. Okay, maybe parallelizing across different cores and other things. But if you are removing weights in this particular manner, where there is no fixed pattern in which you have removed these weights, intermediate points are being zeroed out, you'll not be able to utilize these, say, parallelization techniques or other acceleration techniques to their full extent. Okay, in your unstructured pruning. Whereas what structured pruning does is that if it wants to remove a weight, it will not remove a single weight. It will maybe remove one entire node itself. So your remaining thing, number of learnable weights now becomes 3 cross 2. It's something like this, maybe. Okay. So in a way, what you have achieved is that you have not, you can actually in that case delete that particular set from your learnable matrix, and then you have a smaller matrix to deal with. And based on that, you can then go ahead and perform any sort of matrix multiplication with the input and output wherever it's required. So that's where your structured and unstructured pruning comes into play. Structured pruning will perform pruning on the basis of an entire filter or entire node. Okay. When I say filter, I mean filter for, you say, convolution layers. So if you consider convolution layers of say 3 cross 3, and suppose you have say 10 such filters. Okay. So what it will do is that it will delete entire filter at once. Okay. It will not be trying to zero out individual weights inside a filter. Okay. Right. Whereas unstructured pruning will prune out individual parameters other than the entire filter. It will use different criteria for doing that. We'll see one specific way of finding out unimportant parameters. Okay. And this will be able to perform a much better, in terms of, say, filtering, because it will not remove entire filters that still might contain some good properties. Rather, it will zero out the unimportant regions within a filter, maybe zero out into individual cells within that particular filter. Okay. Right. However, in that cases, you will not be able to remove that particular set of parameters from your matrix that you have, learnable matrix. Instead, you're only able to zero out those places, and which, as a result, you'll not be able to utilize maybe fully any sort of acceleration techniques in those cases. Okay. Right. So we'll look at one structured pruning example and one unstructured pruning example, and we'll appreciate how these two are functioning differently, but the target goal is still the same. So what we will do is that you have say convnets initially. We'll try this on convolution networks. So you have convolutional layers, and any convolutional layer will have some filters of size, say 3 cross 3 or say 5 cross 5, and so on. And any layer, if you remember, say, I think even in your, say, assignments, you have created convolution layers. You remember you generally create convolution layer in this way. So you have, say, 3, if your input has 3 channels, you give input size as 3, and you mention something over here. Maybe you are mentioning 16 over here, and then you give the size of your filter, say 3 cross 3 maybe. Okay. And then say stride padding, other things you mentioned. Okay. So this generally represents the number of channels in your input. So if your input is your RGB image, you have 3 channels. This actually refers to 2 things. It refers to the number of output channels that convolution layer will produce, and also it refers to the number of filters this particular convolution layer has. So if I mention 16, it will have 16 3 cross 3 filters. Okay, and each of these filters will perform convolution on your entire image. That's given, but you'll have 16 such filters. So model pruning using, say, structured pruning, what it will do is that it will maybe delete, say, 2 or 3 of these filters. So you're left with, instead of 16 filters, you may be left with, say, 14 filters. Okay, depending on whatever criteria it's using. Okay, and okay, so let's start with this process itself. In order to find out unimportant, or say in our case, not very, redundant channels. Which instead of redundant, we generally consider, say, relative importance of channels. What this particular paper does is that it will calculate the sum of absolute weights of the channels. When I say channels in this particular case, please consider this as filters actually. Okay, individual filters. So if you have 16 filters, you add the absolute values of the weights that are currently there, because this is a trained network. You already have a trained network, so these weights are already learned for every layer. So for each filter, you get the absolute sum of absolute weights, and the general idea is that the higher the sum of absolute weights for a given filter, more effect it will have on your output of the model. Okay, because compare a filter which has maybe a lot of zeros and maybe a few ones. Okay, and compare it with another setup that is fully filled with, say, 1 2 3 5 6 7 8. Okay, if image comes to this particular filter and the same image goes to this particular filter, the output of this particular filter will be small because contains maybe mostly zeros and very few ones compared to a filter which has large number of values that are larger than say 1 or 0. So the assumption that this particular paper makes is that if the sum of the absolute values of a particular filter is large, I'll consider that particular filter as important compared to a filter that has very low value for this particular sum. And this will be the basis that this particular paper uses in order to prune a few filters. Okay. So the steps include that for each filter in a given layer, in a given convolution layer, you'll calculate the sum of the absolute kernel weight. And then what you'll do that you'll sort all of these filters. Suppose if it has, in this particular case, it has 16 filters. So you'll sort them by that particular sum that you have. And what you'll do is that you'll prune out the smallest sum values and the corresponding feature maps. Okay. So if you have 16 such values, you have arranged them in, say, your increasing order. You leave out the first, say, 7 filters, and then, and again, this is a hyperparameter, how many, or maybe it will depend on the target compression that you're wanting to achieve. Based on that, you will decide on the number of, say, high value filters that you'll retain or the number of low value filters that you will discard. Okay. And
So how
that
we
way
got
you'll
that
prune these
number?
filters. Which number? 7.
No, any number like you told, ascending order we set, and which we have a lowest value, we will
So
remove
suppose you have 16 3x3 filters,
that.
okay, at a particular layer. For every filter, you're finding out the sum of absolute weights. So you have some values in these places. 3x3, you have 9 parameters.
Got it.
You take the absolute value and add them.
Mhm.
Okay. So that way you can get one single value for every filter.
Means sum is minimum, means it will impact minimum, like that.
Yeah. So when you're discarding the filters which have very low this absolute
Sum.
values, yeah, sum of absolute values, you're effectively what the paper claims is that you're discarding only those filters that does not have much effect on your output.
Mhm.
Because in general their overall absolute weights, whether it's positive negative does not matter, it's not very high, so it will not have that much effect on your output as compared to the other layers which have larger say absolute values, and that's the basis on which they discard these smaller values.
Got it. We can also take mean of that numbers.
You can also take mean. Yeah, there are various options available. This is a paper from 2017. I think they used this sum. I think they showed that this sum was working well for them. You can try out different things. It might differ from network to network, also might differ from task to task. Okay. So right. So you'll discard these, you'll do these things for all the layers, and after that you will be able to basically be able to, you'll obtain a, say, much smaller network in terms of number of parameters that you have. However, this will severely affect the performance of your network because you're not removing individual parameters in this case. You're removing individual filters itself. Okay. So it might affect the network performance. So what you'll do is that you will we'll try to recover this performance somehow. Okay. So there are different approaches to do this. What you can do is that you can prune filters of multiple layers at once. So what you can do is that instead of considering one layer which has 16, say, 3x3 filters, you consider, say, 2 or 3 layers. So total number of filters that you are looking at a single time will be much larger. So that way you'll be able to judge better what are higher valued and what are lower valued important or unimportant filters. And then you discard them. And once you discard them, and you basically complete all the layers, once you've done completing this thing, you retain them until the original accuracy is restored, or you're close to the original accuracy. Okay. The other approach is you do it layer by layer, or you can also do it, say, filter by filter will be tricky, but you consider, say, layer by layer, and you prune filters for a particular layer, recover the performance, then you move to the next layer, again prune it, again recover the performance. This continues iteratively till you're done with the entire setup. Okay. And what this helps you to do is that since you're going layer by layer, you always try to ensure that you are retaining as much of performance as possible. Okay. And also, I mean, you can also try this thing out where you'll consider multiple layers at once and then try to regain the performance. Again, move to the next set of layers and prune it. Again, try to regain this performance. So with this, you're again, it's still structured pruning. So when you're pruning entire filters at once, and that discards a large portion of your parameters. Right. So that's the general idea behind your model pruning using say structured approach. The other idea is unstructured pruning, where you do not restrict yourself to removing entire filters at once. Rather, what you'll now do is that you have even say for filters or say fully connected layers, you will have some set of weights, and you will try to zero out the unimportant weights in your given filter, so that at least in terms of computation you can you have a sparse matrix sort of, and you can either use a special storage for sparse matrices, or you can maybe also I mean in terms of computation also, because multiplication with zero is extremely fast. I mean it has been optimized in many of the say CPUs or GPUs, whatever you have. So in that terms also your amount of computation requirement has also getting reduced. But then it's not a structured way of deleting weights. So in terms of say storage, you might not get that much of an improvement, but in terms of say processing, you might get significant improvements. Okay, right. So this is operating at a fine grain level, allowing for more flexibility in which weights you're pruning, and rather than say removing entire neuron channels or layers. Okay. Now we'll look at a basic approach for this thing. Obviously, in all of these cases, you consider pruning once your model is trained, whether it's unstructured or structured pruning. And then you maybe after pruning, you may try to regain the lost performance through some retraining or some fine tuning. Okay. Now, obviously, if you're looking at individual weights, just like in the previous case, you're looking at individual filters. You need to find a way of obtaining or identifying maybe important and unimportant weights. Okay. A very common way is simply looking at the magnitude of these weights. Okay. Just like in the previous case, we were looking at the absolute sum of the values within that particular filter. We'll be considering the magnitude or the absolute magnitude of the individual parameter values in this particular case. And the idea is still the same. A weight which has a higher value will have a greater impact on any of the outputs compared to a weight which compared to a parameter which has a lower value. Okay. So we'll try to retain as much of the higher value weights as much as possible while discarding as much of the lower valued or very close to value zero parameters. Okay, so magnitude-based pruning assumes that the weights with smaller magnitude contribute less to the model's output, so they are comparatively less important as compared to the weights which have a higher magnitude. So again, what we'll do is that say whenever we are looking at any particular, either we look at a particular layer or we may consider the entire network as well, and we'll sort these weights in terms of their absolute values. Okay, and we'll apply some threshold, maybe depending on how much compression we want to achieve. Okay, or maybe with some prior knowledge that getting say more than 50% compression might significantly hurt your performance, so you don't attempt that much, you attempt maybe something less. Okay. And based on whatever hyperparameter threshold that you come up with, you set those values that do not follow the threshold to 0. And effectively what you're doing is that you're because you're zeroing out a particular portion, say if you have say a fully connected layer, if you have zeroed out say this only has say 3 learnable weights only, if you zero out this particular thing, all connections from here will also get zeroed. So in a way it has a cascading effect. Without deleting a node, you're basically zeroing out the intermediate outputs maybe for some of the weights that you have. Okay. Now we generally use a binary mask which represents say which of the weights have been zeroed out. So maybe you zero out those weights which have been zeroed out, and the others whatever value is there, because if you multiply with this particular mask, those weights that have been zeroed out will become 0, and for the other cases whatever value it had, you multiply with 1, that value still remains the same. Okay. So a mask is updated to reflect the pruning process. Basically pruned weights are set to 0 and the rest are left unchanged. Okay. After pruning, again obviously in this particular case again you will encounter some loss in performance. Okay. So again you will perform some sort of fine tuning even in this particular case. You will train the model on this data set, but you will only update the non-pruned weights. Okay, and which we can already identify the non-pruned weights because we already have a mask that shows us where in which layer which of the weights have been pruned. Okay. And that way you're now whenever you're trying to recover the performance, you're not allowing the pruned weights to learn anything new. Only the remaining weights are learning something new so that the performance can be recovered. That way you're reducing the parameter requirement while also performing close to what the original method was performing. Okay. Yeah. Any doubts up to this point on model pruning? Okay. If not, we can move to the next part, which is you're performing compression using parameter quantization. Okay. And as I explained earlier, the general idea is that you want to shift these weights that are generally, say, using, say, floating point 32-bit representation to some lower representation. So you're moving from a high precision to a lower precision, which obviously will result in some loss of information, but we are willing to do that because we are willing to reduce the amount of, say, computation or storage required for a particular model. Okay. So some terms that will come in handy for parameter for quantization, we can have a scaling factor. We'll look at a very basic way of parameter quantization. There are more complicated approaches. We are not going into that. So you have a scaling factor, which we'll see how to basically compute that controls. Yes.
Sorry, sir. Any example like high precision and low precision?
So as I said, so suppose you have a 32-bit representation, floating point representation, and if you can replace it with 8-bit integer representation, the storage space will reduce, or the computation will reduce by a very large margin.
That would be 1/4 of.
Yeah, I mean, see, it's just not just that. I mean, a floating point operation itself also is a very complicated operation compared to even a simple same size integer operation. So
Yes.
it's a manifold decrease in your computation requirement.
So like a number which can be stored in 8-bit from 32 we can replace to 8-bit and it will be
Yes.
Okay.
Yes, exactly. That
This
will
is-
quantize your model and reduce the storage as well as your computation requirements as well.
Okay.
Right. So, okay. So another term that comes into play is a 0 point. We'll see how to utilize these two things in order to achieve your quantization. Okay. And 0 point, as the name suggests, is basically the real number 0 in the quantized domain. Whatever, once you shift it, whatever it will happen in your quantized domain, that will be the new 0 point. We'll see how to calculate these things. Okay. So there can be two types of quantization. One is the asymmetric quantization, other is the symmetric quantization. Okay. Symmetric quantization is basically you fix the 0 point in the quantized domain to 0 and you distribute the rest of the weights on both sides of it. Okay. So it's symmetric that way. In asymmetric quantization, you're not necessarily fixing the 0 to the center of that range, quantized range. So that way it's different. Okay, and we'll see how, depending on symmetric or asymmetric, we can have different definitions or different calculation process for the 0 point. Okay, right. So for asymmetric quantization, what you will end up doing is that you'll calculate the scale and the 0 point first. The scale is the max and min value of the real valued samples that you have. See, suppose your weights that you're trying to quantize, they have a range between, say, -5 to, say, +2.5. So that will be your max value and your min value. And okay, I mean, you'll obviously have to get the gap between those things. So, right, fine. And you take the quantized range, whatever you're considering. So this is the asymmetric case, you're not zeroing out. So maybe the quantized range is, say, I consider only weights between, say, 1 to 3. Okay. So 1, 2, and 3, this is suppose the quantized. After quantization, you will get values in terms of only 1 and 2 and 3. So what you'll do is that you will take this entire range, and the idea is that you will divide it into this 3 part. So this first part will get replaced by 2, second part gets replaced by first part gets replaced by 1, then by 2, then by 3. Okay. So effectively, what you have done is that now you consider the entire network. Wherever you get a value between -5 and say -2, you replace those values with, say, 1. And wherever you get a value between, say, 0 and -2, you replace it by 2. And wherever you get a value between 0 and 2.5, you replace it by 3. So that way your reducing the variability that's present in these weights, and you're representing them by some integer numbers. Okay, obviously this will have a major effect on your the output that you're generating. So you'll have to do some sort of a updation or fine tuning so that your model performance still can be recovered, sort of, because you're replacing information by a different type of information altogether. Okay. So for your asymmetric quantization, you have S value calculated in this way. You're taking both the ranges, and this ratio gives you the amount of compression, the scaling factor that you're doing for this particular setup. And the 0 point will be calculated in this manner. You have your quantized range minimum, whatever the minimum value in this case, suppose it's 1, and you subtract the minimum value of your real number divided by your scaling factor. Okay, and so basically you are then pushing your Z close to one of the ends, basically, to get maybe from 0 to 1 or 0 to 2 to one of the ends of your quantized range. And then what happens that obviously you'll have to you are trying to replace these floating point operations with integers. So even if you're not getting an integer value, you will in all of these cases will try to round it up with the nearest integer. I mean, you round up the Z to the nearest integer. Scaling factor, obviously, it will be as it is, whatever it's there, right? And so this is some typical examples of the quantization range. So I mean, the min and max values are anyways the minimum value, maximum value of the current data that you have, not necessarily the entire 32-bit range of floating point that you're using. So in this particular case, you only have weights between -5 and 2.5. So minimum will be -5 and maximum will be 2.5. The quantized range for say will be say if you're using an 8-bit integer or 8-bit signed or unsigned integer, depending on whether it's symmetric or asymmetric, you'll use something mainly ranging between say 0 to 255 for 8-bit unsigned integer, and for 8-bit signed you will be ranging between say -128 to 120 values. Okay, we'll do something similar for symmetric as well, but for symmetric we'll fix the Z as 0. And your scaling factor will be calculated in this manner. You will take the absolute value of the min and max, and then take the max among these things. Suppose in our previous case we had -5 and 2.5, so your max will give you the absolute value. So absolute value 5 will be higher, and your say quantized range max was in our case 3, so you have some scaling factor in this way. Okay. Right, and you have 0. Once you have these two with you, S and Z value, whether it's a symmetric or asymmetric case, what you can do is that you can take any of the weights that you have and perform this operation. What is the operation? This is the 0 value and this is scaling factor. You divide the real weights, real number, by the scaling factor, round it up, and you add it to your Z, okay, which is anyways rounded up to your Z. So that way you get a quantized value to replace your existing weights. Now, if I look at this particular steps, if I look at this process step by step, so what do? I first of all count or basically find out the corresponding min and max value in the input data, which is the weights in our case. We find out which type of quantization we want to do, whether it's a symmetric quantization where you have a signed integer, or maybe an asymmetric case where you have an unsigned integer of say 8 bits. Then what you do is we calculate the Z and the S, that is 0 point and the scaling factor, as we have described in the previous slides. Okay, and then what you do is that we have Z and S, so we basically convert all the weights that we want to quantize using these Z and S. Okay, and so that we can now represent them using say an integer 8 representation or an unsigned or integer 8 representation compared to say floating point 32 operation. So then what you will see is that we'll see whether the performance of the quantized model is good or not. If it is not good, maybe we'll either try to say use a different scaling factor, or maybe what you can do is that maybe we can fine tune this model a bit using these quantized values only, and try to come up with try to recover some of the lost performances. Okay, and that's the general idea behind, I mean, very basic way of performing parameter quantization. Okay, there can be problems related to say quantization, because you are actually in this case replacing it by a different number altogether, because at the end of your day, at the end of the day, your network is basically a function, and more specifically it's basically a matrix, and at any stage you're performing matrix multiplication. So if you're replacing the individual values within that matrix, maybe the output changes by a very large extent, so maybe you might have to do some sort of a fine tuning. in order to maybe recover the performance that you have lost. Okay, so there are different ways of quantization. You can um, do a quantization after, say, your post training and stop there and not do anything, or maybe you can do a quantization during training as well. So you update the weights, but you don't update it in terms of real values, you update it in terms of quantized values. So different ways of approaching the same situation, but the core idea still remains the same of how you can quantize these values. Okay, great. The next idea which we have covered in detail is the, you want to do compression, but through knowledge distillation. Okay, it involves, say, a smaller, simpler model that has a similar performance as a complex and larger, say, teacher model. Okay. And what a teacher model does is that even with the network, student network still trains on, say, the data to perform some sort of classification, maybe. The teacher model provides sort of a guiding light, or say a soft target for it to achieve to. So for example, if the student is predicting cat correctly, but what the teacher does is that for any given image, it's also producing some probability for the other classes as well. So if you have, say, cats and dogs, so you have, say, and say car, you have, say, a 0% possibility that a particular image is a car, and 0.8% possibility that a particular image is a cat, and this is supposedly your dog. So yeah, yes.
So it's is it similar to the knowledge transfer learning we learned earlier?
Yes, it's the same thing. We are just using that concept under, say, model compression, basically. So if you have a situation like this, your student model, if it's only training on, say, your classification laws, it will try to give a very high performance to, say, your class for your for your cat, but it might try to zero out the other things. So what we try to do is that we say that don't zero out the other ones. We try to get the same distribution as the teacher, because the teacher was trained on a much larger, complicated model. It was able to give some importance to a chance that it might be a dog as well, and zero importance to, say, your that particular image being a car. So that way you are sort of giving it a soft target rather than a hard target of achieving. So this was the idea which we covered in much detail. We'll look at two different types of, say, knowledge distillation. We had specifically looked at this in very detail. Basically, you had two teacher network. You pass, the teacher network is pre-trained. You have a teacher network and a student network. You pass the same data to both of them, and you get their output logics, and you apply a distillation loss. We had specifically looked at the Kale divergence loss in that. And that is actually a response-based knowledge distillation. There is another type of distillation which is known as feature-based, which, as the name suggests, rather than looking at the logits, you look at the intermediate layer outputs and try to make them same. So in your response-based logits, you are trying to make the logits similar for the student and the teacher. In your feature-based distillation, you are trying to make the intermediate layer outputs as the same, which is slightly tricky because your student and teacher in this case are different models, because the teacher model is a complicated, much larger model. So the intermediate outputs also will not match necessarily between the student and teacher. But then what you're trying to do is that in each intermediate level, you're trying to achieve some similar features from both from the student model, similar to what the teacher was producing. Okay. So we'll see, both of these techniques. And there can also be other versions of it which combines both of them. Okay, so response-based knowledge distillation we have already seen, where we were simply trying to make the logic of the student as close as possible to the logics of the teacher. Okay, and we have discussed this in very much detail. The other option that we can look at is the feature-based knowledge distillation. So your deep neural networks, if you have looked at such a scenario, if you take a trained CNN and you
by this knowledge way, I'm not able to understand how it is reducing the layers.
Yes. So it's not directly reducing the layers. What you're effectively doing is that you're training a smaller model that has the same power as a larger model, same performance as a larger model, so that you can now replace your larger model with your smaller model. Okay. So it's not deleting any layers or parameters, but it is replacing a larger model with a smaller model. Okay. That way it's compressing your model. It's not directly compressing it, it's indirectly reducing your requirements in this case.
Okay. लो एक्सपीरियंस का बंदा वो सेम पोजीशन पे हायर करो.
Exactly. But you're providing some knowledge transfer to it. Just say even industry also you have knowledge transfer, so that is able to at least perform close to the previous guy. Okay. So right. So we have now feature-based knowledge distillation, right? And we are doing this because intermediate layers also extract very good, say, information about or features about your given, say, image that you are passing on to it. Okay. And we want to make the intermediate representation similar for your student and teacher network. Okay. So instead of simply looking at your say logics. So what you do is that you will try to get the intermediate features, okay, and will try to map it so that you can now compare these two features. Now mapping will be a difficult task because, as I had already described, your student model is maybe generally a smaller model. Say you have m and n layers, and maybe m is maybe significantly less than n. So how do you then, you don't have a one-to-one, you might not necessarily have a one-to-one correspondence between the features from these two levels. So what you can do is that you can maybe you can club the output. You can take the output of, say, a set of teacher layer and then map or say compare the output of your first student layer to the output of this particular layer, these two combinations of layers. Okay. Because the number of layers in student models will generally be less than the number of layers in your teacher model. So that way, what you're doing is that you are, again, we still have not solved the problem. The output itself will be of different sizes. So we'll see how to deal with that situation. And at the end, once you have both of these outputs of the same size, we'll convert them to the same size. Then you can simply do, say, a simple MSE loss or whatever loss, to make them similar. Okay. Right. So one very important factor that will come into play is some sort of a transformation function. First of all, this selection will be, sort of like a hyperparameter, which set of layers you want to map to a single layer for your student network. And then another thing that will happen, that needs to happen, is to transform these feature maps, which are of different sizes, into a common space where you can compare them. Okay. So it's not given away, but anyways, so what you can basically do is that you can take the output from this particular layer. This output, suppose this is a convolution layer. So you have some, say, let's consider a single channel only for now. You have some 2D output of some width and height, and you have an output from here which has again some width and height, which may be different. What you can do is that you can either take say a mean of this, all the values in this particular output, or you can take the max, or you can take the sum. You can do the same thing over here as well. I think I had looked at a paper which basically takes the sum of the values. Okay. And that way, now for this particular channel, you have one value, one fixed value, and you have another similar value from the teacher model, and you try to make these two similar. You apply some loss, you apply cross entropy, not a cross entropy loss, but say MSE loss or say L1 loss, and try to make them similar. Now you're doing this for all the intermediate layers. Okay. And in a way, what you're trying to achieve is that whatever intermediate features that your individual, the teacher model was trying to get or getting in the intermediate layers, you're trying to get similar features at the student model level as well. And obviously they'll not be exactly the same because the sizes itself will also be different. And this is also a valid way of performing knowledge distillation. Okay. So there are two ways that we have seen. One is you simply use the logits and try the final output, try to match the final output, or maybe you try to match the intermediate outputs, okay, which is much more trickier because the intermediate outputs are not necessarily of the same size. Okay. So these are two ways you can apply knowledge distillation for this particular setup, and through this we are indirectly performing model compression. Okay. Another approach is the low rank decomposition. I'm pushing a lot of terms today. You can maybe refer to these things and slowly go through the related concepts about these particular setups. Okay. And the low rank decomposition is one of my most, I find it very interesting because it's a very simple setup where you have, say, a very large matrix of say you have, say, 10 cross 10 matrix. And what you try to do is that you replace it by, say, a 10 cross 2 matrix and a 2 cross 10 matrix. And effectively, it's if you multiply these two, you still get back your 10 cross 10 matrix. But this one had 100 parameters, and this only has 20 plus 20, which is 40 parameters. Okay, so you're trying to get back the same weight, but using less number of parameters. Okay, that's why I find it very interesting. You can utilize this in different ways actually. And in fact, we have a paper that utilizes this concept in incremental learning as well, to reduce the amount of extra information that you're trying to put in for every given new task. Okay, the core idea is that you want to perform some sort of a low rank decomposition of your given matrix, so that you can get these two lower rank matrices. Okay, and then you can represent your matrix approximately using a multiplication of these two matrices. This may not be an exact decomposition because of various factors. The primary being that suppose the rank of this particular larger matrix was say 10. So you remember 10 rank means that if rank of a particular matrix is 10, that means it has that many independent row vectors or column vectors. Okay, and if you have that many independent row vectors and column vectors, it means those are the directions, or those are the important properties of your given matrix. Now, if I represent a matrix which has a rank of 10 using two smaller matrices, if you remember, if I have a 10 cross 2 matrix, what is the maximum rank this particular matrix can have? If you remember, it's actually very straightforward. The maximum rank will be the minimum of these two values. So if rows and columns, so the maximum rank this particular setup can have is 2. The maximum rank that this particular setup can have is again 2. So you're representing a 10 cross 10 matrix which has a rank of 10 using two matrices which have rank of 2 only. So that means you're bound to lose information. That's why whenever you're showing this particular setup, this is always an approximation. Whatever lower rank you're coming up with, lower rank matrices representation, that will always be an approximation. What we do is that we take every layer, okay, and perform this sort of a decomposition of this particular layer. And once you have done this decomposition, say suppose you have done your standard, your singular value decomposition, you get something like this. If you remember, you can also maybe refer back to your SVD things. We'll not go into the details of SVD because that's not within the scope of your, deep learning. But for your understanding, I'm giving you this concept so that you can appreciate how this thing is working. So you will have a setup something like this. SVD basically gives you three matrices. You have one U matrix, we have a diagonal matrix in the middle, and another matrix V. Okay, and your U matrices are basically, again, these are both U and V will be orthogonal matrices, and your sigma will be a diagonal matrix. And if you, by default, SVD will give you a setup where you can actually recover back your W, because you have not reduced the rank. You'll see that we don't reduce the rank in your standard SVD, but you can actually modify this particular setup to get a lower rank approximation for this given thing. Okay, and we'll see what we'll do. So first of all, in order to perform this decomposition, we have your W. So we'll calculate these two products. We have W transpose W and W transpose, and this will give you individual two matrices, and we'll calculate the eigenvalues and eigenvectors. Okay, again, we'll not go into the details of eigenvalues and vectors. It's beyond the scope of our current course. Okay, right. So the eigenvectors of W transpose W will give you the columns of V, and the eigenvalues of W transpose matrix will give you the columns of U, and the sigma matrix, which is a diagonal matrix, where only the diagonal entries will have some values and the other entries will be 0, will contain the square of the non-zero eigenvalues of W transpose W. This will be actually superscript, or W transpose. So effectively, you have specific steps which you can directly decompose your W into U, sigma, and V transpose. Okay. Once you have that, I have still not achieved my solution. What I need to do is to come up with a lower rank approximation for W, for which I'll have to reduce the rank of these matrices. And how can I do that? I can do that by looking at your diagonal matrix. So diagonal matrix will have some eigenvalues, some non-zero diagonal values. Suppose it has 10, then 5, then 6, then 7, then 8. Okay, no, sorry. This will be 8, 7, 6, 5. Generally, it's in the descending order. You arrange them in the descending order. So you have the higher valued eigenvalues first and the lower valued eigenvalues later. What I'll do is that, suppose I'll take only the first two eigenvalues. Okay. Now, if you remember eigenvalues or eigenvectors, these generally represent the most important components of your given matrix. Okay. So, suppose if your given matrix has say has 10 rows and 10 columns, your eigenvalues will give you that you'll give you eigenvectors will be say 10-dimensional vectors, which will give you some of the which will give you some of the important properties of that given say matrix, and the corresponding eigenvalues of those vectors. Depending on the magnitude of these eigenvalues, you can decide which one is a more important eigenvector as compared to the lower important, less important eigenvector. So what I can do is that the more important eigenvectors generally store better information about your given matrix from which you have obtained them. So, in order to get a lower rank matrix, I will retain the higher rank eigenvalues only. Say I'll take the first two values, okay, setting say k as 2, okay, and set the others as 0. Now, imagine a situation where you have a matrix here, and a matrix here. And this is suppose your m cross k, this is k cross k, and this is k cross n. Okay. Now, if I zero out, I keep only the first two entries, okay, and I zero out the others. Effectively, what you're doing is that you're when you perform this matrix multiplication, all the rows after the second, see, when you multiply these two things, you still get m cross k because you have m cross k cross k cross k. Okay. So if I zero out everything after the second eigenvalues, you will effectively only get an m cross 2 matrix. All the other values, say from 3 to k, all those other columns and rows will basically become 0 because you have zeroed out a portion of your matrix multiplication. You can try this out. Definitely, you go when you are going to this lecture, you can just simply try this out. So what you're doing is that you're reducing this m cross k matrix into an m cross 2 matrix effectively, and this particular matrix will get from say k cross n gets converted to a 2 cross n matrix. Okay. So assuming that the rank initially was more than 2, now you have now come up with a approximation for W using vectors that have a lower rank than the actual rank of W. Okay. Now with this, obviously this is already an approximation with a lower rank. This has become even more of an approximation. Now what I do is that I have this lower rank versions of my matrices. I either combine your sigma matrix, multiply it with the U matrix, or I multiply the sigma with the V matrix, and I come up with a lower rank approximation of W, which has U dash into V dash. Okay. And once I have these, so you have effectively reduced your W, which was a very large size matrix, into a product of two smaller size matrices. Okay. And what I can do is that initially, if an input was getting provided to W and the output was calculated using this matrix multiplication Wx, now what I'll do is that I will simply perform the same multiplication using multiplying x with V first and x with then with U, because effectively this U and V multiplied will give you back the W. Okay. So what you're doing is that this U and V are of much smaller size now. Okay. So the number of parameters that you will have to use to store these set of values will be much lower. Okay. So if you look at this particular setup, you have a weight matrix of size say 1024 into 512. You had these many parameters, and you now learned a low rank decomposition of the particular W, and you learned two matrices of size say 100 of say, if you're taking a rank of say 100, if you're taking say 1024 cross 100 matrix and a 100 cross 512 matrix. These are the number of parameters that you have, and if you add them up, the total number of parameters is significantly lower at 1,53,000 compared to 5,24,000, which is a 3.4 times compression that you're achieving. Okay. So in this particular section, you have seen how we have reduced the number of parameters by basically splitting the W into smaller sized matrices, and then it does not affect at least the operation on any given input. The operation still remains same. You're still performing W into X. Rather, in this case, you're performing U into V into X, okay, which requires much less number of computation. But you have reduced the parameters by a very large margin. Yes.
Yes, sir. how we can choose k is equal to 100 or k is equal to 50? Any
So that depends on how much you want to reduce the reduce the parameter usage. So if you look at the initial weight matrix, it had a size of 1024 cross 512. So 104 cross 512 means that it has a maximum your rank possible is 512. You take the smaller one always. Okay. Right. So now what you'll try to do, you'll come up with a smaller rank so that you can reduce the number of parameters. So you'll take one value that is less than 512. Obviously, you won't take something more than 512. Otherwise, it defeats the purpose. So now what you can do is that you can, ideally I can take maybe k equals to 1. Okay. But what will turn out is that, remember that when you reduce the k, say originally maybe the rank was 512. If you reduce the k, you're losing out on a lot of information. Okay. So you have to balance between compression as well as loss of information. So you will try maybe something, maybe say 250. Okay, and you do this for all the layers, and you get some performance on some validation data, and you see that the performance drop is not that much. Okay, so initially if the performance was 89%, you're still getting 88%. Okay, so you'll now try maybe something lower. Maybe you try with say 100, and you see that still the performance only drops to say 87%. So that's fine. I mean, if you're okay with a 2% drop, you'll go ahead with say 100, and you'll not go any further maybe. Or maybe you can also try maybe k equals to 50, but then you see suddenly the drop becomes a very large. So it's sort of like you'll have to try out different. There's no quick fix for getting a k. It's sort of again a hyperparameter, and it will also depend on how much compression you want.
Okay, sir. Okay.
Okay, I'll not go any further in this class. Any doubts up to this point? We have seen a lot of compression techniques. Each of them, you can obviously create one that is hybrid, and each of them are targeting a different, utilizing different ways of reducing the parameter size. Okay. And you can obviously come up with something that is a hybrid of these things.
All these compression.
Yes, I cannot hear you, Rohan.
Can you hear me now?
Yes.
So all the compressions would lead to some sort of accuracy impact on
Drop.
accuracy.
Yes.
Okay. So is there any criteria that which one is the least out of these in terms of, if you have to have a trade-off, which one is the best that can do the compression or something like
so
that?
it will depend actually. Say some of these compressions, as you would have observed, are also very I'll not say time consuming, but are very complicated to achieve. Okay, for example, say your low rank decomposition, if you want to achieve this, you want to do this for every weights that are there. So for example, if you have a large network, say with 50 or 100 layers, and every layer has say 100 or so filters, so for every filter you have to do these things. So low rank decomposition may be a choice when you maybe have, you have enough time or say enough computing power to perform all of these compressions. It drops down to what kind of compressions you want to achieve. I've seen people only work on simple pruning to achieve a very large compression of say 10, or say I've seen people with also 20% compression achieved over there, which then solves that purpose. Any sort of compression where you are changing the values of the weights, say for example, whether it's quantization or say for example in this case low rank decomposition, you can expect a larger drop in performance. Okay, compared to a situation where you're simply zeroing out some of the unnecessary bits. So that is one thing that you can keep in mind maybe. And ideally for any given setup, you want to maybe try out different you can also refer to some existing work on say compressions and see which type of technique is giving you how much compression for a given say setup, and based on that also you can decide on it. It's purely on an experimental basis, and maybe in some cases how much effort you want to put into compression. So all of these factors will come in. I'm not sure if there is any quick fix of deciding any set of nodes to decide on which compression to go for.
And the dropout that we have, which is a separate concept,
Yes.
but that also achieves zeroing out certain nodes and all. Does
Yes,
that
but
does that
one thing
also
that happens with dropout is that you don't your while testing your dropout becomes basically inactive. So
right?
your dropout happens only during training, and during testing it becomes a identity sort of a function itself. So you might get better performance through dropout. I was just trying to give an example through dropout, but effectively you're not reducing any of the parameters or zeroing out any of the parameters during inference time, which is when finally your model comes into play, say after deployment or so.
Okay. Thank you.
Okay, I'll stop the recording then.